Now in this video I will show you what happens in a circuit that is just a little bit more complicated than the one that I did before. So in the previous video I had the same uniform wire and that was the only thing that was connecting the two sides of the battery. Now I'm gonna make a change. Okay, I'm gonna take this portion and I'm gonna replace it with a different kind of wire. Okay, this is gonna be now a wire that has a smaller diameter, so it's gonna be from here to here and from here to here. Okay, so the diameter of my wire in this section is smaller. Now, okay, the fact that the diameter here is smaller means the following thing. If you look, I'm gonna go back to my theory. I know, okay, I'm gonna start with experiments again. I know even if I change the wire here, I know from experiments that the current is the same everywhere. So I still have the left side to be a constant. Now here's the thing, in this case, this is no longer true, right? So let's erase this. Let's see what happens. I'm gonna rewrite it because I want to rearrange the terms. So I'm gonna write this as the electron density times the electron mobility. Now these two depend on the material, and I will, for this problem, I will assume I'm using the same material to construct this circuit. This means that I'm keeping those two constant, and the reason is I'm using the same conductor, the same material for the wire. Now what is left here is the area and the strength of the electric field. Here's the thing, now the area is no longer a constant. The area here, let's say the thin part of the wire, the area in the thin part of the wire is much smaller than the area of the thick part of the wire. Now if the current is constant and the area decreases, then to compensate for that decrease of the area, the electric field will have to increase. And this means that the electric field here I will have to draw a longer arrow for the electric field in the thin part of the wire. Okay, so the first step for me was to find out what happens to the current. From experiments I know that this is constant for this circuit. Now from the theory and the fact that I'm using the same material for both the thin and the thick wire, means that it's only the area that will affect the strength of the electric field. And when the area gets smaller, the electric field will have to increase to compensate for that. So now I have my electric field arrows around the wire. So what I see here, I have some short arrows and a long arrow in the thin part of the wire. Now I have to make sure that my charge distribution reflects the fact that here I have a stronger electric field. So let's see. From 4, I go to 3, 2, let's say, what did I do before? Before I had a 1 plus here and 0, okay, and that told me from 4 to 3 a difference of 1, 1, 1, 1. Now that is no longer consistent with a stronger electric field in the thin part of the wire. I do need to make this difference to be a 2. So I'm gonna start by adding 2 here, and then I'm gonna maintain this difference of 1. And that means I'm gonna add some more pluses here. Let's see. From 5 to 4 a difference of 1, 4 to 3 a difference of 1, 3 to 2 a difference of 1, 2 to 0 a difference of 2. Now the fact that I forgot to do these two. The fact that I have a difference of 2 here compared to the difference of 1 anywhere else, this is consistent. This difference of surface charges is consistent with a stronger electric field in the thin part of the wire. And now, because I have symmetry in this circuit, I'm gonna go from 0 to -2, and then -3, -4, and then -5 over here. So because the strength of the electric field here is the same as that one, here I have a difference of 1, here I have a difference of 1 between those 2 points. So this is how you will approach the problems where you have a thick portion of the wire, and there is a part of the wire that is thin. And I want to finish this video with one note. Now that you see this, and you see that in the thin part of the wire I have a stronger electric field, this is a very simple model for a resistor. When you add a resistor in a circuit, the electric field inside the resistor is significantly greater than the electric field that you have in the rest, in the wires that allow you to connect the resistor to the battery. So as a final note, let's do, say, this portion here, consider this to be a simple model. The thin part of the wire, this is a simple model of a resistor. And the analogy is, in resistors you have a stronger electric field than the rest of the wires.